Okay, Ms. Howard's chemistry class. We're working on Unit 5, and this is Part 5, electrons in the periodic table. Now, we've talked about the electrons, we've talked about wavelength and light, and now we're ready to move on to really focus on C5a. I'll explain the use of chemical and physical properties in the historical development of the periodic table. I will use the periodic table to identify and explain the properties of chemical families, including the alkali metals group 1, alkaline earth metals group 2, transition metals, all that low part in the middle, the halogens group 17, and the noble gases group 18. And finally, C5c, I will use the periodic table to identify and explain periodic trends, including atomic and ionic radii, electronegativity, and ionization energy. Oh, joy of joys. So Roman numeral number 2, the periodic table, and I do have a song for you, but of course I can't play it right now because, no, it's just not working with the whole video within a video thing for me yet. So, letter A, the history. In the early 1800s, scientists tried to classify the known elements. They tried to figure out, all right, we've got these elements that we know, let's classify them. So the first guy that we really know of is Dobrin, a German chemist, and he came up with the idea of the elements being grouped by properties or trends. So he said, hey, let's put them together, like elements together. Newlands came along in 1863 and said, okay, that's pretty good. Let's organize them by atomic masses, and he came up with this thing called the law of octets, which means that he noticed that similar properties were repeated, it seemed like every 8 elements. But the big dog came along in 1869, a guy by the name of Dmitry Mendeleev. He was a Russian chemist and teacher, and he put the elements in order by their atomic masses, and he found that when you put them in order that way, they naturally fell into order by the properties, as long as you left some blank spots for some elements that he thought hadn't been discovered yet. So he's really close to something called the periodic law. But at this time, they didn't know what the atomic numbers were. And our periodic table today is organized by atomic number. He had them in order by atomic masses, so there were some discrepancies there, things that didn't quite work out. He said their properties were caused by their atomic masses or their mass numbers, and that they were periodic, which means that you could see a trend happening, and then it would start all over, kind of like when we have first period, second period, third period, fourth period, through 8th period. And the next day you start it all over again. First, second, third, fourth, fifth, sixth, seventh, eighth, and you start it all over again the next day. He left, this is huge, he left blank spots where he thought that there were undiscovered elements. And he said, okay, it's not fitting perfectly here, so I'm going to leave a blank spot because I think there's something that's going to fill in that blank. And sure enough, within 15 years, those blank spots, people had discovered those elements and they filled in the blank spots, which is just pretty incredible. There were, again, still, even with those, there were still a few slight discrepancies because he had them in order by the mass number instead of the atomic number. And here is the lovely Dmitry Mendeleev, who is in serious need of a hairdo. And that's what his original stuff looked like when he was working it out. All right, number 2. In the early 1900s, a really young man, a young scientist by the name of Henry Moseley, he rearranged them. He actually figured out what all the atomic numbers were for the known elements at the time, and he rearranged everything by atomic number. And what that does is it tweaks it just a little bit so it really works better. So he came up with, or they created at this time, the periodic law, which says the properties of the elements are periodic functions of their atomic numbers. Okay, what does that mean? It means that, hey, if you look at the properties of the elements like boiling point, melting point, if you look at densities, if you look at how big the atoms are, that they're periodic functions. Those things kind of repeat. You can see a trend, and then you start back over at group 1. And you see a trend go across the periodic table, and then it starts back over at group 1. You see a trend starting across the table, goes to the end, starts back over at group 1. That's what he's talking about. All right, what I have are some different pictures of some really weird, strange periodic tables. What we see, or what you see on the wall, or what you see on the chart that I gave you, is not the only arrangement of the elements, but it is the most common and the most well used. So I have some interesting things that are on here. Here's the Stowe periodic table. Here is, this one always reminds me of a spaceship somehow. I feel like the Starship Enterprise, yeah. It's a spiral periodic table. We have the Mayan simply because it's almost, like the circular calendar of the Mayans. So here you have the Mayan periodic table. And I love this one. This is the pictorial periodic table. It's got pictures of, what types of things to use this in. Like, element number 15, phosphorus, is found in bones. Calcium phosphate is found in bones, and so you see a picture of the bones there. Let's see, oxygen, it's got a picture of clouds and sky. Oxygen's obviously in the air, and so on. Why is there toothpaste on the fluorine one? The next one is just another one, and it's got, everything's color-coded. So you've got all the different groups. You have the nonmetals on the left of the zigzag, on the right of the zigzag line, and the metals on the left. The alkali metals are yellow, so you can see that right there. Again, just different ways of showing the periodic table. I like this one. This is the periodic table of the superheroes. So again, somebody just said, hey, this is a kind of cool arrangement. Let's see if we can put these in here. I don't know if they have similar properties if you go down the group, but you guys, I'm sure you are, some of you out there are big fans. So all I know with this one is, these are ones where the superheroes or the villains, they actually had that element within their name, like aluminum or cobalt, or I wonder if Krypton has Superman on it. No, it's got a dog. You guys figure that out. What's a dog with this? Is it Super Dog? I don't know. This one is the periodic table of video game characters. You guys might even recognize more of these. You can pause this at any time, and so you can look at the pretty picture here. And this one is the periodic table of the Xbox games. So again, you'll probably see some that you guys recognize. And you can look these up online. You can just type in periodic table of Xbox games, and I'm sure it'll pop up. And that's it for this period. Okay, this is Miss Howard's Chemistry class, Unit 5, Electrons in the Periodic Table. We're on the PowerPoint section number 4. We're still talking about electrons, so we're working on C6E, the electron configuration. And we're ready to talk about some more ways that we can figure out where those electrons are in the atoms. And number 5 on your notes is the Pauli exclusion principle. And that basically says, and it's kind of a no-brainer, but you get your name in the book for some of these things. No two electrons can have the exact same 4 quantum numbers. Now, that means you can't have 2 electrons occupying the exact same space, which, again, makes sense. And this will be on the back of your, I can't remember which page it is in your notes, but it's the back on the drawing. Number 6 is the Aufbau principle. And this one says that electrons are basically lazy, and they're going to fill the position with the lowest possible energy output that they can. So they're going to, before they go and fill out a really high energy orbit, they're going to fill in the lower energy orbits first. So the electrons in an atom are lazy, and they'll fill a position in the atom which is of the lowest energy level, beginning with energy level orbit 1 and the S sublevel. And because of that, when we have our SPDF chart, it's not just doesn't just go straight across 1s2, 2s2, 2, and so on. You have to use the diagonal rule to fill it all up. Number 7 is Hund's rule. When electrons occupy orbitals of equal energy, one electron enters each orbital until they all contain 1 electron. So pretty much what that means is they don't pair up until they absolutely have to. So you see the spiffy little Orbits Hotel, and it's got 3 rooms, X, Y, and Z, the X-axis, the Y-axis, the Z-axis, and they're not going to pair up 2 in the X and 1 in the Y and none in the Z. They'll have 1 in the X, 1 in the Y, 1 in the Z, and then they'll pair up when they have to. And what that does is that allows the electrons to stay as far apart as possible. And that's simply because like charges repel. They're going to get as far away from each other as they possibly can. And number 8, knowing all of this information, which you will know all before the test, you're going to know all this. Knowing all of this allows us to write an electron configuration or a description of where all those electrons are. So 1s2, 2s2, 2p6, 3. I have the song for you. So here we have the diagonal rule, and you fill these in order. Just follow the little golden arrows. So you have 1s2, and then you go back up to the top of the next row, fill in the 2s2, 2s, and that can hold 2 electrons. Go back up to the top of the next row. Fill in the 2p. It can hold a maximum of 6 electrons. Then go to the 3s. It can hold 2 electrons. Then go back up to the top and fill up 3p. But before you go to the 3d, you go down to the 4s. Why? Because the 4s has less energy in it. It requires less energy of the electrons than the 3d does. So that's where that rule comes into play that, they're basically lazy. They're going to fill up the lowest possible energy level first before they go to a higher energy level. So number 9, the electron configuration of an atom's highest occupied energy level. That means the outermost orbit determines the atom's chemical properties. Oh my gosh, that's huge. The electrons in the outer orbit are called the valence electrons. Circle that word, put a star beside it, put a big flashing neon sign on it. But the valence electrons, the electrons in the outer orbit, determine the chemical properties. So how do we know if things are going to react with other things? We look at the valence electrons. So the electrons in the outer orbit, or outer energy level, are called the valence electrons. That's a big one. Now, here what we have is a lovely picture showing all 4 of those quantum numbers. So if you take the 2p with a little x beside it, the 2 is the principal quantum number, which those are the numbers that run down the side of the periodic table, 1, 2, 3, 4, all the way through 7. The p is the angular momentum quantum number, which basically tells the shape. Is it an S, a P, a D, or an F? The little x is the magnetic quantum number, which tells you its orientation in space. Is it along the x-axis, the y-axis, or the z-axis? And then the little up arrow or down arrow, that's going to tell you the spin. Is it spinning one direction or the other? Usually opposite spins is what they're talking about. But you see where all the 2's are up here? All of those you would count the electrons up, and that would be the valence electrons. So the 2 is the outer orbit, and it's got 1, 2, 3, 4, 5, 6 little arrows, and so it's got 6 valence electrons. There's an easier way to tell how many valence electrons. All you have to do is look at the periodic table. But you can also tell just by looking at the electron configuration. Right. There are some exceptions, and I'm going to run through these really, really fast. And the exceptions come about because they allow for more stability. So, stability is more important and more natural than even using the lowest possible energy level in there. So copper is an exception. You would expect it to have 4s2, and then it fills in the 3d, and it's got 9 electrons. But in reality, it's 4s1, and it fills up the 3d level with 10 because it's more stable that way. So you have several of them that are like this. Chromium has a unique, kind of an unexpected electron configuration, and you won't have to know all of the exceptions to the rule. But just so you know that there are some exceptions, and that's due to stability. Now, when you talk about ions, you have something where you've altered the number of electrons, so you have an unequal number of protons and electrons. So the atoms gain or lose electrons to become stable. Again, that word stability is really important. Why are they reacting? They're reacting to gain or lose electrons so that they become stable. When they're stable, it means that they have somehow become iso means same, isoelectronic, so same electrons, valence electrons, as the noble gases. Group 18, way over on the right, the noble gases, they all have a full outermost energy level, or they have this magic number of 8. For some reason, 8 electrons in the outermost energy level is stable. And so all of these other atoms are trying to reach that stability level by getting the same outer energy level as the noble gases. So if you look on the pretty picture here, when all of the group 1 metals, they have 1 valence electron, so it's easy for them to lose that electron, and they end up having 1 more positive charge than negative charge, so they have a +1 charge. Group 2 has 2 valence electrons, and so they end up losing 2 electrons and end up with 2 more protons than electrons. Group 13 cover up the 1, and that 3 tells you it's got 3 valence electrons, and they tend to lose 3 electrons. And group 4 tends to, it can go either way. Lose 4, gain 4 electrons. Group 15 Group 15 has 5 valence electrons, and it's easier for them to steal 3 negative charges from some other atom, and so they tend to form an ion that has a negative free charge, 3 more electrons than protons. And the same goes all the way across. Now we have group 16, and they tend to steal 2 electrons from somebody. Group 17, the halogens, they tend to steal 1 electron. And then you have the noble gases that really don't do anything. They have a 0 oxidation number because they don't really react with anything. Okay, when you talk about the ion electron configuration, that's when we've stolen some electrons from somewhere, and so we have to add in those electrons. Now, so if we have an oxygen ion, it's in group 16, so it's got 6 valence electrons, and it was 8. So it's going to steal 2 electrons from somebody. And because it steals 2 electrons from somebody, it becomes isoelectronic with neon, so it becomes stable by doing that, by being in a chemical reaction or a chemical bond with another atom or 2. Now, what you see here is you can write out and this is an oxygen ion, so it's got 2 more electrons. So you can write it out as 1s2, 2s2, 2p6. Yeah? It's got 2 more stolen 2 electrons from somebody. Or you've got a little bit of a shorthand method where you write helium. So people get tired of writing the first part repeatedly, so they just put helium, and then it's 2s2, 2p6. So they do some interesting things like that. And we'll look at that. If you look in the back flap of the chemistry book, this is how they're written. Okay, so let's see what we have here. Oh, we have some lovely periodic table patterns. Here is hydrogen, and it's 1s1. It has 1 electron total, 1s1. So it's in the first period. It has an s orbital shape, and it's in the s block. The pretty yellow section is the s block. And it's in the first column of the s block. Now, if we do sulfur, it has 16 electrons. So we have 1s2, 2s2, 2p6, 3s2, 3p4. Okay, the p section could hold 6 of them, but you only had 6 of them left. Now you notice the stuff in blue? That's going to be the outermost energy level or orbit. So count up the 1, 2, 2 plus 4 is 6, so it's got 6 valence electrons. It's in group 16. So cover up the 1, it's got 6 valence electrons. So valence electrons are there. Those are called the core electrons. They're just kind of in the central area. We're in science. We name everything. Now, if we want to make a shorthand notation, we would go with neon, because neon's the core. It goes up to there, and everything's full up to the core, and then we add on the valence electrons. So that's just a different way of writing it. We'll probably focus on not worrying too much about the shorthand configuration of it. All right, you can also see these written in more than one way. Rather than just writing them all out, 1s2, 2s2, 2p6, all to the side, you can also see them written down. So if you look at letter A up here, this one is the ground state. It's got 1s2, 2s2, 2p6, 3s2, 3p6. So it's got 8 valence electrons, right? And it's got 8, 9, 10 core electrons. That's what you're looking at. Now this particular one, we're taking this gas, and we're heating it up, and we actually look at that, one of those 2s electrons jumps up to a 4s spot, and so it becomes excited. And when it becomes excited, it can't maintain that excitement for very long. It's going to ultimately give that excitement off as light, and it drops back down. That electron that was jumped up to the 4s drops back down to the 2s where it was originally, and emits that photon. It's just another way of writing stuff. And we're ready to end here.